So for those of you watching at home, Masha says hi. For those of you watching at home, you're going to get a slightly different voice just for this one short section of the kinetics lecture. So we're going to figure out how do we find the rate law for a particular reaction. Previous lectures in this chapter have been about like looking at reaction mechanisms and looking at elementary steps and things like that. Now we're going to start to figure out mathematically how can we determine the rate of a reaction. So generally, you run that reaction several times using different initial concentrations of each reactant. And then from run to run, you vary the concentration of one but keep the other one constant. And then you measure the initial rate and compare the rates for the different runs to determine the exponents in the rate law. So to refresh your memory about what a rate law looks like, rate law equals K A to the X B to the Y, where these are your reactants. Okay, so your rate is equal to some constant value times the concentration of one reactant to some unknown exponent times the concentration of another to some unknown exponent. Okay, so now we're going to look at how do we solve for these exponents mathematically. All right. So for a given reaction, this is a, how about this? That's a Y. I can't make, the question was, why don't I make it B? Equilibrium lectures, you'll see we use B for something else. Okay. All right. So here is a rate law experiment where our reaction is, let's just say it's A plus B makes AB. So we're given this data below. We set our initial concentrations, and we measure the initial rate. Why do you think we might want to only measure the initial rate? Let's take a wild stab in the dark. So the final rate would be at equilibrium, so we want an initial rate. No, not about it. It's more like this is where it's at its fastest, right? So it's going to change the most at the beginning, but it's going to be in a measurable way, in a way we can see. So we have run 1 where we set our initial concentrations at half a mole per liter. Then in run 2, we keep B constant and change A, and we look at the effect on the initial rate. And then in run 3, we kept A constant from the beginning, and we doubled B, and we can see the change in rate. So unfortunately, I wish we had done this where the two slides would be like next to each other. So you're going to have to sort of flip back and forth as we're doing this. Or you could do like this, where you have, oh, see, I have this, oh, I have the single set. Oh, so it's fine for you guys. It's just for me that it's messed up. All right, here's your strategy. So you look for the runs where one concentration is kept constant. So for example, if I look at run 1 and run 2, what stays constant between run 1 and run 2? What concentration? Yeah, just shout it out. B. So my initial concentration, that's what that not mean. This not now down at the bottom means initial. Okay. So my initial concentration of B is constant. And then what happens to my concentration of A? It goes up by what factor? Double. A doubles. And if A doubles, what happens to the rate? It also doubled. Rate doubled. Rate doubles. So I know that if I double A, I double my rate. So what exponent must it be for A if we go back to our rate law? I'm putting in, somebody shout out a color. I heard purple first. So I kept B constant. What exponent goes in there? Yeah, 1. So I know now that X has to equal 1. So we haven't gotten into what that means yet. Just know that the exponent, which means the order of the reaction, is 1 with respect to A. So, and then between 1 and 3, what's held constant in reactions 1 and 3? A. So A naught is held constant. B naught doubles. What happens to the rate when you double the concentration of B? Quadruples. So what is the exponent for Y? 2. So if I want the overall rate law for this reaction, I know it's R equals K concentration of A times concentration of B squared. Yeah, Eli. So the statement was you can solve for K by plugging in any of these points, and so without looking ahead, Eli looked 2 slides ahead. But without, so which is awesome. You saw the future, right? So that's exactly what you do. Absolutely exactly what you do. Okay. Now, there is I just did it very simply. Some of you may enjoy math. I know I have, how many of you are in or have taken BC Calc? 1, 2, 3, 4, 5, 6. How about 7? Yeah. 7 people, so more than a quarter of the class. And many of you who are juniors may do that next year too. So that's like the high, yeah. A lot of sarcastic cheers just went up from the crowd. Okay, so now here's the math behind it. You're just setting up this equation. You have the comparative rates, R2 over R1, is equal to the 2 rate laws, right? So R2 equals the rate constant times A2 to the X, B2 to the Y. The rate 1 equals K. The K stays the same. So this value, K, is constant at constant temperature. So you can change K by changing the temperature. But as long as we're doing those reactions at the same temperature, they're good. Awesome question. So won't the reaction itself change the temperature of the solution? The answer to that is yes, but we're looking at sort of idealized. So we'll have it in some isothermal reaction vessel where any heat that's released will be sucked out. Okay, so now we have our R2, D2, 2 times 10 to the minus 3. I hated myself. Even as I said that, I hated myself. All right. All right. As I'm waiting for this to actually work. Oh, come on. So I'm waiting. What do you guys think of the new Star Wars trailer? Iffy? New lightsaber? Yeah. The made-up ones? Yeah. Yeah. All right. So I'm kind of with Avery that I thought it looked good, but I'm skeptical. Yeah, the music and the Millennium Falcon got me really excited. All right, so all right, so what's that? So the question is John Williams doing the music for the new movie? Yeah, it's gonna be him or Zimmer. Yeah. It will be John Williams, but I think they're just going to use a lot of the same music. Okay, so the K crosses out, and I could have plugged in here, but I forgot because I was distracted by Star Wars. So this becomes 2 equals, and what did we hold constant between 1 and 2? B, so this crosses out. So we have the concentration of A2, which was 1 to the x over 0.5 to the x. So if I do this, what can I simplify 1 to the x over 0.5 to the x as? Two to the x. So 2 equals 2 to the x. Now if you're really into math, how can I solve for x? Yeah. Yeah. So ln2 equals x ln2. Or you can do logs, you can do natural logs. So x equals 1. Sorry, I got very excited. I saw a former student out in the hallway. I actually saw my neighbor out in the hallway. But, okay. A former student of mine, or a former student is a neighbor of mine. Yeah. Okay. Now, if we do the same thing, I want you guys to do the same thing over here. Derive R3 over R1 to determine y. How do I get from here to... So the question was, how did I get from 1 to the x over 0.5 to the x to equals 2 to the x? Okay. Because you can take the x out, right? So if you do it all out, it should look like what I have up on the board. It's fine. All right. So guys, most of the time when you do things like this, if I give this to you on a test, you won't have to do this because it should be something very straightforward, like 1 doubles and the rate quadruples, or 1 doubles and the rate octuples. Is that a word? Has some octupulation. Goes up 8 times. All right. So those are easy exponents to figure out. We're not going to do it so it's difficult for you to figure out. Okay. All right. So how do we find k? Eli, how do we find k? You plug in 1 point and solve for the constant. I always like to find the one that has 1. So if our rate law is this, let's be efficient with our time. Which run, 1, 2, or 3, do you think it would be easiest to find k for? I'm going to go with 3. Why is it easiest for 3? Because you get 1 squared. You don't have to do any squares. So 6.4 times 10 to the minus 3 equals k times 0.5 times 1 squared. So k equals 6.4 times 10 to the minus 3 over 0.5. So 1.28 times 10 to the minus 2. If I did my mental math right. All right. So you just plug it in. Now, one of the disadvantage of not doing the rest is, I don't know if Mr. Hamill talked about the units for K. All right. So K definitely has units. Did he? Anybody has he talked about? Yeah, the units for K vary. I'm gonna look back for a second. Okay, well, let's find the units for K, just because this has been historically like a multiple choice type question, and students really, really struggle with it. So what are our units? What are unit? Shout out a color. Pink, I heard pink. Pink is going to be hard to see, yeah. Blue, all right, blue. What are the units for rate? Moles per liter per second. So that equals K. Now in this case, I have moles per liter times moles per liter squared times moles per liter times moles per liter squared. So I have, bless you, moles per liter per second equals K times moles cubed over liters cubed. All right. So yes, K is your units for K are going to be different for 0, first, second, and third order reactions. So depending on your exponents, your K is going to have different units. So yes, well, let's just do it this way. I like multiply both sides by get K by itself. Liter squared over mole squared second. So units for K equals liter squared over mole squared second. So we make these arbitrary units. K is just a factor that makes it work, so we can give it whatever units we want. You didn't talk about the units for K, did you? All right. It's not bad to hammer it home a little more. Oh, sorry, I was just talking to Mr. Hamill. Okay, so now we're looking at example 2. I want you guys to find the rate law for this reaction, the reaction between A and B. Remember, we're assuming the reaction's this. But it does not have to happen in one elementary step. So we have all this data that's going to help us. Use the method we talked about, not the crazy mathematical method if you don't want. But you can use the crazy mathematical method, but it's on the next slide. So I'd like you to do it the sort of more straightforward way. So this one's a little tricky. You had to solve for A first. So if I do that method, I know that in between run 1 and run 2, B stayed essentially the same. 0.201 and 0.199 are essentially the same. So if I have run 1 and run 2, right? So B stayed essentially the same. All right. So guys, B stayed the same. K crosses out. So I get, well, let's look at R1 versus R2. What did you notice about R1 and R2? Essentially the same. So R1 over R2 equals 1 equals, whoops, R2 is 3 times as big, right? 0.6 over 0.2 to the x equals 3 to the x. Well, what number can x be such that 3 to the x equals 1? 0. So x equals 0. What does that mean? A is 1, right? A does not matter in this reaction. So the concentration of A is independent of this reaction. What's that? No, Y is not 0. So I will show you how we can find B in a second. But are you guys with me on finding this? All right. So we found the exponent, like how big of an impact does A have on the rate is what we found. And it has 0 impact on the rate. All right. So Eli asked the question when I had it muted. Are we going to assume X and Y are always whole numbers? We'll give you cases where they're always whole numbers. But, I think on the problem set, are they all whole numbers on the problem set too? There are cases where it's not. Yeah. It's on the problem set. Yeah, you have calculators for that. So in real life, yes, absolutely, it can be not a whole number. So now people got confused because there are no cases. There are no cases where A is held constant, right? So let's just pick one where B changed. So 3 and 2. So we know that this is R2 equals, let's just say 0.44. R1. All right. So I'm simplifying a little bit. Okay, now, if I go back and plug in, I shouldn't have put 1 and 2. I should have put 2 and 3. Thank you. This won't be complicated. We're not using logs or anything. I'm just showing you we can cross stuff out, right? The question was, we don't have to use complicated math. I'm just showing you how we can cross it out. Okay, so for run 2, I have 0.6 and 0.2. And then for run 3, I have 0.4 and 0.1. All right. Now, what can I cross out immediately? Well, you can immediately cross out the case. But now, any number to the 0th power is 1, so the A's cross out too. So now I see that if I go all the way over here, 0.44 over 0.11 is 4 equals 0.2. Is that better? Okay, sorry. I got too excited. I missed a 0. All right, so now 2 to the y equals 4, y equals 2. So now my rate law is R equals K. Well, if it's a to the 0, do I even need to worry about it at all? Nope. K B squared. All right. I don't think I have to do much more writing, although I do have to walk through some more things. The rest of the math, guys, is spelled out for you for the next few things. I want to talk it through, but it's already on your slides. Okay. All right. So here would be doing it all out, not crossing anything out. This is, if you're more comfortable with the full-on mathematical solution, most of the time, guys, you're just going to be able to think, one doubles, what happens to the rate? Straightforward, quick. All right. But if you want to do it this way, you're more than welcome. So I wanted you to see that I can cross the stuff out, right? So I'm ignoring everything else and just getting it down to doubling and quadrupling. The reason I actually had to do it this way, Eric, for this one, is so you could see that a to the 0 is going to be 1, so it doesn't matter. All right. Okay, so now, if I want to find the k for that, well, I have my rate law. You just plug in any single point, and you get the k. All right, there are instances where you might need to use the mathematical approach. This would be a problem set thing and not a test thing. So in this case, I have what's happening to A from run 1 to run 2. Goes up 50% or 1.5 times. The rate, not as much and not like an easily divisible number, right? And then if I keep A constant and look at B, again it's 1.5, but, well, you guys might be able to eyeball this. If this goes up 1.5 times, how much is this going up? 1.5 times. You might be able to eyeball the effect of B, because if this goes up by 1.5x, that's about 1.3 to 1.9 is about 1.5x. So what is the rate law exponent with respect to B? 1. Because if the concentration of B goes up 1.5 times and the rate goes up 1.5 times, it's 1. But to find A, it's a little more difficult. So you would have to do 1.22. It's not that. This looks. Yeah, this looks complicated. But again, let's just walk it through. In this case of R2 over R1, well, that stays constant. This stays constant. So instead of having a nice number you can do in your head, though, 1.5 to the x equals 1.225. So this gets to your question. X, in this case, is a half. It's a square root. So the question is, will you ever have to do it by solving a system of 3 equations? It's possible, but it would be the same thought process, right? You find you'd have to keep 2 of the initial concentrations constant and vary the third. Okay. All right, so that's it for today. You are not. That's Mr. Hamill will finish up with integrated rate laws.